Welcome to another episode of Baz Codes. I'm your host, Big Chungus, and today we're going to talk about timing, chip timing in the Apple II. I have been, as you may know, working on an Apple II emulator this year called GSSquared, and obviously I've done work on emulating the Apple II timing because the emulator's been out there for a while, and it works pretty well. But some elements of the way I handle the timing are admittedly dirty hacks, and don't work very well. Or rather, if you try to tweak other parameters of the system, then they don't work very well. And when I recently added the cycle accurate video, some more cracks kind of appeared in that framework. And thinking about Apple II GS emulation, which is on the roadmap, it has a much more sophisticated clocking regime because it's trying to be an Apple II, but it's also trying to be, a more modern, much faster computer. So I realized I needed to revisit the way I handle the clocking. Before now, I've kept track of Apple II system timing simply by incrementing a CPU cycle counter. This has the benefit of being simple and straightforward, and works okay for most purposes. And it assumes exactly every cycle is exactly the same length, and that's where some of the issues start to creep in. Because in an Apple II, not every cycle takes the same amount of time. So let's take a few steps back. In an Apple II, all of the system timing is derived from roughly a 14 megahertz clock, which is called in the schematics appropriately 14M. It's actually 14.31818 megahertz. And this is I got from the reference in Understanding the Apple IIe by Jim Sather, which is the most accurate and thorough book relating to Apple II hardware functions. If you're trying to do anything with an Apple II, if you're trying to make Apple II add-on cards, oftentimes if you're trying to write software, if you're trying to emulate one, it is absolutely by far the best reference available. And it was available back in the early 80s, which is pretty impressive that this guy actually took the time to dissect the Apple IIs to such a degree that he was able to produce this amazing reference work. And this beat anything that ever came out from Apple themselves. Probably the only other person with this level of detailed knowledge about the Apple II would have been Steve Wozniak himself. So aside from the 14M clock, and I know you're thinking, well, wait a minute, the CPU in the Apple II is 1 megahertz, right? Yes, that's correct. But how it gets to the 1 megahertz is the story here. There's a number of signals generated from the 14M clock. There's the 7M clock, which is used in the video system. There's the color reference signal, which is also used in the video system. There are RAS and CAS and Q3, which are used in RAS and CAS are used for the DRAM refresh timing. It's roughly a 2 megahertz. Oh, I should go back. 7M, roughly 7 megahertz. You probably figured that out. The color reference, roughly 3.58 megahertz. RAS and CAS, roughly 2 megahertz. And then, of course, we get to the CPU clock, roughly 1 megahertz, or as some people often kind of abbreviate it, 1.023. Now, none of these numbers that I just mentioned are accurate. The most accurate numbers are in this table. As you can see, they are extremely long numbers of decimal places. And that is a challenge for emulator writers because in the real system, you just have, the clock ticks up and down, the 14M, and you do derive other signals from it, and it's fine. You don't care what the time is. You just do your behavior based on when the clock changes. So the precise amount of time doesn't necessarily matter that much, unless you're talking about the video. But when doing an emulator, you've got to tie all these figures back to the modern computer and the host environment, and make those figures make sense for someone experiencing the emulated computer. And that's the big challenge, and something that I think a lot of emulators don't quite get right, including up to date GSSquared. There's a few key parts of the emulator that need extremely accurate timing: audio generation and the cycle accurate video generation. The cycle accurate video needs to do exactly 17,030 cycles per video frame, basically to draw one, top to bottom scan of the display is exactly 17,030 CPU cycles. And unlike modern computers that are, to have display refreshes of exactly 60 frames per second, or 75 or 120, in some cases, the Apple II video is tied to the NTSC standard for televisions and composite monitors, and that has a frame rate of 59.94 frames per second. Not a convenient number. Now, we can simulate that, but getting to this 59.94 from some of these other numbers, that's the challenge. And it turns out a great deal depends on the precise relationships of all of these numbers. So we're going to take a look at some code I wrote, which was my first pass at emulating this, kind of just starting to do some math and trying to figure out, the best approach. So this program, I keep track of, just cycle counter, like CPU cycle counter. Oh, there's one other entertaining part of the Apple II. I mentioned the CPU clock was 1.023 megahertz. Well, it's not exactly, because it is for 64 cycles, but then the 65th cycle is long. It's another, call it 150 nanoseconds in length. And so you see that's the secondary frequency they talk about here, 0.894. So the effective CPU clock rate on an Apple II is 1.0204. It's actually just a hair slower than that nominal CPU clock. The reason for this has to do with keeping the system clocks synchronized also with the NTSC horizontal beam timing. And WAS needed to add just a little extra time to sync that up. So the 65th cycle of every group of 65 cycles is the 977 nanosecond duration here of the regular kind of CPU clock, plus 2 extra 14Ms. So that he delays the CPU clock by an extra 2 of the 14M cycles, and then proceeds. So, and I think this is something that is not commonly dealt with by emulators as well, but becomes important when you're talking about the Apple IIgs, as I mentioned, which is constantly speed shifting. It is quite complicated. So with that in mind, that's what I was trying to write some routines to do some math around and try to have have a piece of code that emits all of the appropriate timing signals that the emulator needs, based on number of cycles, based on time elapsed, right? And I have to translate emulated elapsed time into real time, us out here in the real world, in order to prevent the emulator from running too fast or from running too slow, right? Let's call it the Goldilocks zone, where it's just right. So back to the code. So that's what cycle 65 is. That's just keeping track of, is this the 65th cycle, and do we need to make it a little extra long? We have frame duration. Now this is a figure, the 16688.083. This is straight out of the Sather book. And then I've got the 14M cycle duration, which I calculate here based on the 14,318,180 hertz rate. Now, if you're wondering about some of these, sorry for the pop-ups. It's, my IDE is trying to be helpful there. If you're wondering about some of the naming here, what I'm doing is I'm converting these values into what's called fixed point. So you're familiar with integers, very simple, just whole numbers, and floating point, which is a way to represent a very wide range of numbers in a fixed number of bits, like 32 bits. And it's floating because the decimal point can move, right? You can have at different points in time in a variable more or less digits past the decimal place. Fixed point is kind of a middle ground between those two, and you predefine a number of bits for the the whole number part and for the fractional part. The reason for this is that fixed point representation, you can do math using integer math routines in your software or in your CPU. It can be much, much faster than floating point routines, which have to take all sorts of things into account. And fixed point doesn't lose accuracy. Floating point, like if you have a very large whole part, you start to lose accuracy in your fractional part. And so I wanted to avoid that, and am just using fixed point. Now I chose 48 bits for the whole part and 16 bits fractional. My first attempt was at 8 bits fractional, and that was not enough. It was definitely not accurate enough. And as we'll see here in a minute, even the 16 bits of fractional isn't quite enough. Okay, so the normal cycle duration, like a normal Apple II cycle, is 14 M's, right? It's 14M divided by 14. So I'm calculating that duration. And then the long cycle, this is the normal cycle plus another 2 14s. And the other thing I'm doing here in this test harness is generating, I'm just ticking through cycles and then updating all the numbers each cycle, and then checking to see where video frames begin and end, because that's the key thing. I need to end up with exactly 17,030 CPU cycles, and that needs to be exactly synchronized to, my video updates up to the host computer. So I then display all of these values that I've calculated, and we'll take a look at that here in a second. And then I just run, an emulation here for 1.12 million cycles, something like that. It just needed to be more than it needed to be more than a full frame and more than a second. So for each cycle, I spit out the numbers, and then I update the numbers, cycles plus. I update the number. Elapsed time is this. So for each tick of the cycle, I update the elapsed time based on either the normal or the long cycle duration. And then if more elapsed time has occurred compared to the frame length, which was this video frame length, then I stick some markers in and take a look and see where I'm at. So I'm going to, if I can find the window. Yeah, here it is. All right. So I ran this and I saved all the output because there's, a million lines of output, and stuck it in a text file, and we're looking at it. So, the in the display here, we're roughly 69 nanoseconds. I'll show this here. 977 nanoseconds. That's our 977. Our long cycle is 1117. Okay, that all sounds pretty good. These fractions look weird. What they are is it's a fraction of 65536. That's your 16 bits, right? So to figure out what that would be in decimal, you would do the following. So 69, let's see, 55134 divided by 65536 is 0.8412. So that's what we have here. 69.841278. This is pretty spot on, except for these last two bits, 71. And my representation loses some accuracy, or the math isn't quite right? And so I'm, 0.08 compared to 71. Now, you may be thinking, well, that's such a small amount, it doesn't matter. Well, yes and no. It normally wouldn't, like if you're just doing a single calculation, you could easily ignore that. But what we're doing is we're doing a running tally, right? So every cycle, we're adding that same number again. And that loss of precision on a single calculation is no big deal. But when you multiply it times a million, for 1 second, there's a million of those. So you have a million iterations of accumulated error every second. And it adds up. If we take a look at, this, okay, the video cycle ended at 17,029 because we started at 0. So that's exactly 17,030 cycles. Okay, that first frame is fine. That's great. 17,030. There. 36, 34, and 60. That's good. These are all looking good. They're still nice round numbers. That tells us we're doing well. Wait a minute. Is this where I forgot to... I may have forgotten to do something. Yes. So here I was... oh, no, I wasn't. Never mind. So I basically had to, at the end of every frame, I am kind of resetting some figures here in order to correct for those errors, kind of every frame. That, I don't know, that doesn't sit well with me. And it's likely that there's going to be any number of other places in the system where I'm then going to have to make those sorts of corrections to the numbers in various other places. So that gets back into the dirty hack territory, and I didn't want to do that. I also got to thinking that, even though this is all integer math and 64-bit computer, every computer now is 64 bits. So these are all just simple integer things. It still felt a little complicated. Now that's how I've been doing it, up till now. I've been keeping track of, nanoseconds, not with this precision. I've just been using, sort of whole numbers. And that's some of the issue with the current implementation in the emulator. So I got to thinking though, and it's like, okay, well, if everything in the system is derived from this 14M clock and is basically just some number of 14M clock, like don't think of it as division. Think of the, the 7M is two 14Ms. The 3.56 is one. Actually, I guess that one is 1/4. So I can't. That's not necessarily an even division. The 2M is 7 14Ms. The 1 megahertz CPU clock is 14 of those, but sometimes 16, right? The extra two. So I started thinking, well, what if we just do it on the basis of counting how many 14Ms have occurred? Now, the timing structure of an Apple IIgs, thinking down the road, is different. It's not the same. It is more complicated than that, but some of the same principles are going to apply. So I think you'll have a clock module where you tick in some number of the the 14M pulses. In the 2GS, I think it's maybe a 28 megahertz clock of some sort. And then there's other types of synchronization that can apply when the 2GS is speed shifting from its 2.8 down to 1 megahertz or something like that. But let's just see what we get when we do that. So I've got a copy of the code here, and I'm just going to start changing this to just count 14Ms. So let's see here. And I'm going to say, let's call it C14M. Well, it's not 1M, it's count. No, that's actually fine. Let's leave that. And when I need to get times out, I'll just do math at the time I need to display it, because I don't need to display it, and I don't need to know like elapsed time in nanoseconds. Really all that often, not compared to how often we're just ticking over the cycle counts. So it makes sense as a trade-off to do some math against one of these numbers or one of these numbers to generate elapsed time when needed. Okay. So I'm going to say that's the duration. Okay. C14M. I might get rid of the elapsed time here. This is a long cycle. Normal cycle. Yeah, that's not right there. AI, thank you. Elapsed time. Okay. If I'm not going to do elapsed time here, I'm going to do at the end of a frame is exactly 17,030 CPU cycles. But if I'm tracking this in 14M cycles, then it's a different calculation. It's 262 scan lines times, and I'll remember that here in a minute. There's every scan line is 64 cycles of 14 Ms. And then there's an additional cycle, the 65th, of 16 14Ms. Okay, so each scan line is 912 14Ms, and then I'm going to multiply that by 262 to get one frame. So that's this number. Let's copy that. Yeah, that's fine for now. Okay. I don't need this frame left over. Frame cycle. Oh yeah, that's counting the number of CPU cycles inside my loop. Well, let's just try this. Oh, I need to make fine entry here. Clocking. Nope, it's called clock hole. Okay. What's wrong? Oh, yep. There we go. And where's my little terminal window? There we go. Okay. Oops. That. I need to make this a little wider. Okay, so this is good. Let's go down and look at cycle 65, right? Because I'm doing 14 increments here, and then, yeah, the 65th. What did I say? 912? Yeah, so this starts, this is the 65th cycle, and then we're at 912. So that's correct. So it's doing the correct calculation. So let's go look at the frame. Oh, I'm not resetting something here, am I? All right. See, 14M. Oh, okay. Let's do it like that. No, that starts at 0, sir. And this needs to be my variable then. All right, so what I'm doing now is I'm keeping a sliding window. Of with the end of the next frame. Yeah. Thank you. Yeah, I don't need that. Okay. Unit 64, next frame check. What? Yes, yes, yes. I've got. Right. Okay, that compiled. Let's see. Let's see, 64. Double check that. Yeah, 912. Okay, we're still there. And then let's go look at the end of the frame. All right, so you can see here that at the end of the frame, we have ticked over exactly 17,030 CPU cycles. And if we now go 34060, yeah, this is all very simple integer, integer math. This is going to be lightning fast on pretty much any computer made after, the year 2010 or so. 64-bit stuff. Yeah, okay, so this is great. I need to calculate maybe my, now I need to calculate the elapsed time. So I do have this figure from Sather, which is, I need the 14M cycle duration. So I've got that here. I already calculated that. So let's do, when I want to print that, the elapsed time, I'm going to calculate it. I'm not going to add it yet. I'm going to multiply it. Yeah, that's right. Okay, so E time. So in fixed point, C14M is calculated as, that's integers. Sorry. This figure is calculated as a 4816. And that's why I'm using these long names on here, is to help me keep the the decimal place straight. When I set this up, I take 1 second. This is a billion nanoseconds. 1 second, shift it 16 bits. That makes it the whole part in my fixed point, and then I divide by the 14M frequency. You do the shift first to avoid loss of precision. If I did the divide, the 1 billion here, it would end up with lower precision before I then shifted it into place. There'd be actually, it would basically be an integer division. I'd have a bunch of zeros where I need data. All right, so I've got that. Let's see if that works. Okay, cool. So I'm now calculating the elapsed time. 977.509. That doesn't sound right. Nope. That is not even close. 977.777 is what it's supposed to be. So, let's look at my figures here. Oh, I'm a dummy. Sorry. 5, I got to convert that back to decimal. 50980 divided by 65536. We talked about this before. All right. That's better. Okay. So that's 977.777 89307. So it's a 10,000th, maybe 100,000th place off. I might need higher precision for this calculation. Let's think about that for a second. It's also possible that the Sather book is not being super accurate. Let's test this. So let's see what the more decimal places gives us. 1 billion divided by 14 is 14.31818. 698412871. That's pretty accurate there. But 16 bits may not be enough to give me an accurate figure here. Now, I could, right? Instead of this is where, I can cheat a little bit. And here, for most purposes, this might be sufficient, right? So in calculating the audio samples, right, I need to divide up 1 second of emulation data into exactly 59.92 frames. And if that's just a 10,000th of a nanosecond, you're wrong. That may make absolutely no difference for emulating the audio. But again, we have the problem of if there was a tiny error, if it accumulated, right, 1/10,000th becomes a 1 after only 10,000 iterations. So I can make this a little higher precision, and I can also calculate it afresh based on the start of the frame. So I can use a higher precision just for the start of the frame, or each frame. Let's see, we can calculate what a much higher precision baseline would be. All right, I kind of like that idea. Let me think about that for a second. So a frame is exactly 200 and some thousand. 238,014 M's. Yeah, so let's take this much more accurate number, and I need to divide that by 10. Okay, 238,944. So this is how long the frame should be, using more precision in my calculator here. So let's go take a look at the end of the frame here and see where I'm at. Oh, well, that's weird. Why do I have a frame already at the very beginning? That's because I need to set this at the beginning. The AI was right this time. Okay. That's better. Do I print those after updating? No, I print them before updating. So this is the one here. Okay. So 16688,154 .5000. Oh, that's interesting, right? So instead of multiplying for frame start times, right? For cycle start times, I will use this multiplication. For frame start times, this is a super round number, and I can just add. In fact, I bet this is exactly 0.5. I can just add the frame start times each iteration and not lose much in the way of accuracy. That is a assumption yet to be tested. Alrighty. So Just out of curiosity, I wish I had a second calculator on this Mac. I can regenerate that if I need to. Or I can copy it. Let me copy it somewhere. So let's clear that. 17,030. What I want to do is calculate the number of frames per second based on based on this. So if this is one frame time, then I'm going to do 1 divided by 166,88154.5. Oh, no, I was going to, sorry. 12848 divided by, see, there's some accumulated error here. So that should have been 0.5 and it's 0.34. So now those are fractions of a nanosecond, and that's not going to matter for audio. So I'm okay with that. I think I'll do the thing where I just add for each frame the frame start time based on that much longer precision number here. This. Frame start nanoseconds. Yeah, it needs to be that. 0.5 is 32,768, which is a 1 followed by 15 zeros. This is, so I can OR that in. All right, so I can do talking about hackery. Frame start. Okay, so I'm going to say into video frame, next frame, into a video scan, next. No. Oh. Okay. This wacky stuff converts the fixed point representation back to what you saw in my display here, like this. It gets the whole part and the fractional part. So frames start at blah. Okay, well, let's just make that and see what we get. Okay. So that is correct. So the next frame starts at there. So what we'll do is we'll set a baseline for elapsed time to this. And then we're going to need to keep track of the where we're at in terms of 14 Ms inside this frame. T frame cycle type much Baz? Okay. Of course, at this point, we have a number of increments here. I could, rather than increment this, I could keep track of. Oh, I could just subtract them when I need to print or utilize. Let's do that. Mm-hmm. Elapsed time. Okay. So I'm going to say cycle 14M equals C14M minus I have the next. I need frame cycle 14M. Next frame check. Okay. That's what it is. Current frame. Okay, current frame is that. Right. No. That. Okay, so what I'm doing is keeping track not just of the start of the next frame in terms of 14Ms, but the start of the current frame in 14Ms. And then whenever I need to print it, what I do is that. Okay. Frame cycle 14M is that. I can. Okay. Frame cycle 14M. And then I can do my multiplication to say oops, not here. Here. And that's backwards. Equals this plus frame cycle 14M times the cycle duration. Alrighty. Now I think we got it. So what I'm doing is I'm using that super accurate like start of each frame, right? Which I'm tracking by just adding this very accurate dot 5.5 figure to each frame, and then I'm using that as the basis for doing the calculation. So my inaccuracy will never extend past one frame or 17,000 CPU cycles. And let's see what, and then it'll get reset, right? So it'll stay within that range. Aha, okay. So this cycle I now have starting at exactly the right time. And this is not right. So how much is that off? That is an odd discrepancy. 16688.4 divided by 2955. 5.6. That's an odd mistake. 977. That seems correct. And yet it's wrong. It's a factor of 5.6 off. Well, let's look at the code here, and particularly this calculation. Okay. So, okay, no, C14M plus equals 16 or plus equals 14. So the elapsed time is the frame start time. Well, maybe the frame start time is wrong. Frame start. Okay, it starts at 0, which is fine for the first frame. Frame cycle 14M. And that's C14M minus current frame 14M. So current frame 14M also starts at 0, which is correct. Minus, okay. So this first iteration, this should just be the, well, let's print. Okay, 14M cycle. Cycles. Frame cycle. Let's make this a little more compact here. What's wrong with you? Unsigned, unsigned, long. You went 16T. What? I did not mean to do that. That's why it didn't work. It wrapped. Overflowed. That's better. All right, so there's that. The principle here was that no matter, it's not likely that even if I add a bunch of bits of precision to my fixed point representation that I'm ever going to get this exactly right. Because these are, frankly, these are some irrational numbers, um, you know, and you're always going to have some amount of error in your representation. If you're talking about just integers, right, and you're not trying to divide by 7 or divide by 14, those are irrational numbers if you remember from high school math, maybe even middle school these days. They're really pushing kids. It's great. Uh, there's always going to be some discrepancy that you're going to have to account for. Uh, And it's really then about what's the best way to address that discrepancy. And that's just a fact of computers. People think of computers as exactly accurate, but sometimes um, the representation, the way you represent the numbers, is the important part. If you try to represent them the wrong way, you're going to have less accuracy than if you represent them a different way. And that's kind of the purpose of this whole exercise, is to say, hey, let's track as absolutely as much as we can using just integers and whole numbers and simple whole number calculations, and then only bring in the precision losing calculations when we absolutely need to, and restrict the number uh, of such iterations such that we don't accumulate error over a long period of time. Okay, so if I go to the next frame, this should actually be, something something dot zero. Let's go check that. That's the first one. The next one, hey, yeah, look at that. So my frame start time is going to be exactly right. Now, this figure is important because in the emulator code, after I run through a bunch of simulated CPU stuff at hundreds of times faster than the original Apple II actually ran, because modern computers are amazing, then I need to sleep. I need to wait for a little bit of time to simulate the, 16 odd milliseconds that would have taken the real thing. So that's how the system works. Basically, I break everything up into these frames. I execute a certain number of CPU instructions. In this case, it's going to be exactly 17,030, plus or minus a bit. We'll get into that. I'm going to have, for the video stuff, it has to be exactly 17,030. However, the Apple II CPU instructions are anywhere from 2 to 8 cycles, and my CPU emulation cannot break out in the middle of it processing an instruction. So I occasionally will have some overruns. Actually, probably most iterations will have an overrun of some handful of cycles, and I have to take that into account as well. But this frame time will allow me to sync precisely real time to emulated time. And that's why this is so important, to make sure that it never loses any precision. So that figure is important. This figure is important. Let's see here. And then, let's go to the end and see where we are. For frames, let's see where I break off exactly. This is elapsed time at nanoseconds. Oh, let's go to 1 second. That's going to be hard to type. There we go. Okay, so this is where 1 second has elapsed, and look at that right there. So that's our effective megahertz rate, right? 1,204,804. That was in the Sather book. Um, right here. 1,020,484. 1,020,484 right there. And uh, if I take this, oh, let's see here. That is what's that figure again for the number of clocks per frame? There. Okay. So 59.9227. I'm not sure that was on that screen. Let's see, 5.92, 59.92. He doesn't show that with greater precision. However, that's essentially the correct figure that I calculated before off screen. So this is going to have exactly this many frames per second, which is exactly correct for an Apple II. And our number of instructions per second was exactly right. So I think we're done. This has actually been a very good exercise because it achieved our goals of generating accurate timing signals that don't lose more and more or introduce more and more error with every frame. And we're going to reset elapsed time wherever I need elapsed time. We're going to clock that on an exactly accurate basis. Looks pretty good to me. I like it. All right. I hope you enjoyed this. Let me know if you have any questions about this. Some of this is a little esoteric. Some of you old timers are going to know exactly all the things I was talking about. But anyway, I hope it was educational. And this is some of the stuff. Yeah, this demonstrated a few things like I liked using little test harnesses to test concepts. The current GSSquared code base is, I don't know, 50 or 60,000 lines of code. And testing algorithms, testing ideas in just little small standalone programs can be a lot simpler than trying to test the concepts in the context of a very complicated existing system. What I'll do as the next step is, I'll monkey with this. I'll work on this some more. I don't think I can sleep for a half nanosecond. So I'm going to have to, do a thing where in my main loop, I sleep for, you know, uh, 0 and then 1 and then 0 and then 1 on alternate frames. That may or may not be required. We'll see. The sleep routine may not have that may not have that level of accuracy. But again, those errors will accumulate. So I'll have to think through that. But then I'll take this and stick it in, start embedding this code back into the emulator context. I'll probably do some jiggering with the code to eliminate calculations I don't need. introduce it back into the main thing, and then we'll see what happens. My goal is to be able to have exactly the right number of cycles for the cycle accurate video, and to sleep the exact amount of real time, and not have the emulator run faster. I want to see this exact 102 whatever it was, 10248. Yeah, that I want to see this exact number of cycles executed per second by the emulator. So have a good one. We'll see you next time.